So I'm aware that this is the last talk of the day. So I will try to be entertaining, and if you get lost, just ask questions as I go along. So topic is, we're back to physics, and I will talk about wave-particle duality. But maybe before I start, I should maybe introduce myself a little bit, because I'm a bit new to this community. So I've been, in the last years, we have mainly been working, I've been involved in quantum computing since kind of beginning of the century, end of last century. So I've been designing quantum computing schemes, and we've dreamed up really complicated setups. And then at some point, we wanted to analyze them, write down Hamiltonian for them, do things with them. And just the physical intuition and what these Hamiltonians could do just didn't fit together anymore. So then I did what my supervisor, PhD supervisor, taught me. If you can't solve a problem, make it simpler. So, okay, instead of making the system more complicated, let's make it simpler. But then it became even more obvious that we didn't understand what was going on. So we made it even simpler. So no more atoms, no more mirrors, just electromagnetic field. And we kind of went really back to the foundations. But it's not that I want to invent a new quantum theory. We just had to ask these questions. And I think now we are at a point where we go back to analyzing quantum systems. But this has to go like you described in your talk yesterday. There is a lot of going back and forth between trying to describe experiments, trying to design them, trying to ask questions, and trying to learn something about the foundations. So, outlook. So this is what I want to do. So what we've been doing in the last years, we spent quite a lot of time working on field quantization, on how do we quantize the electromagnetic field. And in order, instead of doing it in the standard way, we did it in what we called a physically motivated way. And we got quite a lot of results. Then I had a new student coming who said, I want to work on electron transport. He says, I don't know anything about electrons. And a book about electron transport had just quoted one of our articles. And then the idea came up, maybe we can do the same with quantum mechanical systems, what we did with photons. So then we applied a physically motivated quantization. I had a kind of idea what will happen, but it became a lot more interesting than that. But I'm not sure what people will think about it. Okay, so this is the main idea. In the standard quantum physics approach, what we do is we try to find canonical variables, and then we impose canonical commutator relations. But this is not really an easy task. If you look carefully at a lot of quantum optics textbooks, sometimes it's E and B that are the canonical variables, sometimes it's E and A. But when you use the vector potential, you used to do it in a certain gauge. So things are not as straightforward. And then you also quickly realize that most quantum opticians, when they write a new book, they copy the guy before, and then everything goes back to just one or two people in the world who have been their teachers. So in our physically motivated approach, what we try to do is to have a more direct way of doing things. When quantum mechanics first came about, people didn't have many experiments to go on. Now we have a lot more experience with photon scattering, detectors clicking, so we can try to get to the same results in a more direct way. Yeah. So what I will do is we will identify the independent states of the classical systems, and then we will map them onto pairwise orthogonal states because they are classically distinguishable, so they have to be also distinguishable in the quantum world. And then we find Hamiltonians, and the guiding principle will be consistency between quantum and classical physics. Of course, most of you know that that's not as easy, but that was our naive idea when we started. Okay, so let's start with the electromagnetic field. I will leave out a few details since it's late and more details are in the papers, but ask questions if you go along. So our starting point was where also all the quantum optics textbooks start with Maxwell and Maxwell's equations in free space. And these are 4 equations, and we know that we can remove the magnetic field vectors. And then we end up with a wave equation. And actually, when Maxwell wrote down his equations for the first time, people didn't know about electromagnetic waves. So the really big discovery related to Maxwell's equations were the electromagnetic waves. So that's where when you ask the physicists, what are the solutions of Maxwell's equations? Electromagnetic waves, yeah. But what D'Alembert had done, okay, I come back to this other one. So what D'Alembert had done about 200 years earlier, he had found a very elegant way of solving wave equations. And instead of writing down the wave equations, what he noticed is you can factor the second order differential equation and write it in this way. And in order to solve that, what you do is you solve this bit and put that equal to 0, or you use this bit, this 2, and make that equal to 0, which is much more straightforward than electromagnetic waves. So that means anything that moves at the speed of light, either to the left or to the right, so that the x derivative and the t derivative are related via the speed of light, solves Maxwell's equations. Yeah. So I skipped one slide, but let's go back. So what we did is when we started in 2016, we first looked at this equation, looked at traveling waves and quantized those in a straightforward way. And it was more because the chapter in the paper, which was about two-sided cavities, became longer and longer, and said, maybe this interests other people as well, let's make it a separate paper. So we were surprised that there was quite a bit of interest in it. But in order for a lot of problems in quantum optics, or when we design devices, we're interested in the local description of the electromagnetic field and not in waves. If I have an atom, that atom is much smaller than the wavelengths, and it acts locally with the field. So what we did more recently was looking at these solutions of Maxwell's equations. And so what I'm saying here is that anything that travels at the speed of light, left or right, is a solution of Maxwell's equations. And that includes localized wave packets. Yeah? So we will take these localized wave packets of light as our starting point for quantizing, and then derive everything from there. And we call them blips because they are short. But if you ask my collaborators, blip stands for bosons localized in position. Yeah. So some people probably know already where I'm going. So what we are assuming is we are having local carriers of light. We know they move at the speed of light. And in order to quantize or to assign them pairwise orthogonal states, we use second quantization. We assign them annihilation operators. They are bosonic, as we will see in a minute. And they now have parameters you have, in order to distinguish them, we need operators for left and for right moving blips. We need to specify what polarization we are having. So these are 2 different types of blips. And then we also need to say where the particle is created, where along the x-axis. So we think of the wave packets like people queuing for a bus, and when the bus comes, then the whole queue moves away. Okay. So we also know that they have to have bosonic commutator relations. So we try to make as little assumptions as possible. But these states that I get when I apply an AS lambda dagger operator to the vacuum state, I get a single excitation at position x. But this only describes single excitation at the x position with S and lambda if they are pairwise orthogonal. Yeah, so if I can distinguish, so it only has a meaning that I'm at x if I can distinguish something at x from something at x prime. So they have to have, the overlap has to be a delta function, which automatically gives me bosonic commutator relations. Okay, good. So now we have the Hilbert space for light. We have annihilation operators and creation operators. What I can do is I can do a Fourier transform to these local excitations. And then what I get is I do a Fourier transform in X. So I get K-space solutions. K goes from -infinity to infinity. I have two polarizations. But now I have this extra parameter that tells me the direction of propagation. So K is no longer the wave number. So what we have done by introducing these local operators is we have doubled the Hilbert space that is usually used to quantize the electromagnetic field. It's necessary because you really need, as you can think of, if you have something that's localized, we need all the K's from -infinity to infinity to localize it. But we have two types of particles now, namely photons that move left and photons that move right. Yeah. Okay, so these blips are not particles themselves because their commutator relations have delta functions in them. So we now have two different ways of saying what are the carriers of light. You can describe light by as monochromatic waves and superpose those waves so that these are blips in K space. Or you have localized wave packets, these blips, and put many of them together, and then you can construct single photons out of them, single photon wave, wave packets, and so on. So, but just having a Hilbert space and states is not enough. We also need a Hamiltonian, we need observables. But well, we know what these blips are doing because they move at the speed of light. Yeah. So in the Heisenberg picture, we now know that some AS lambda of x at time t has to have the same expectation value if it's at x and t here and moves in this direction. Then at time t0 it was here. So that means this operator has to be the same as this one, and that's enough to derive the Hamiltonian from it. Yeah. So we can go back. And what we find is a dynamical Hamiltonian. It looks maybe a little bit strange. What we can do is instead of having the d over dx here, you can write put in the delta function and the derivative of a delta function. More or less what this Hamiltonian is doing in position space, it's taking a blip here, making it disappear, and recreating one next to it. And then in this way, you end up with a particle that travels at the speed of light, and it's emission. And you can see that it's emission because when we transform it into momentum space, then it becomes diagonal. It doesn't have any d over dx in there. And it looks almost like the one we always have. But the difference is that we now have this extra parameter for left and right moving light. And the eigenvalues of these Hamiltonians are positive and negative. And normally we try to avoid negative frequencies. But there's a simple argument of why we need these negative frequencies. Because think of a wave packet that's traveling to the right. What you can do is you can take a movie of it. And then you can take the movie and play the movie backwards to someone. And they won't be able to say whether the wave packet is traveling this way or it's traveling in this direction. And you can't tell in which movie when the time is going forward, when it's going backwards. But in order to accommodate all of this in the same Hilbert space, you need to have generators that have exactly the same format when you change t to minus t. Yeah, because the generator for the movement in this direction is analogous to the Hamiltonian that generates this dynamics backwards in time for for a wave packet that moves in the opposite direction. So it has to do with the time symmetry, why we need to have positive and negative eigenvalues. But then the dynamical Hamiltonian usually has to be the observable for the energy. But I think this is the problem because we want energy to be always positive. But then what we can do is we can show that for k larger than 0, your energy, your dynamical Hamiltonian is equal to the energy. And in the Hilbert space of the negative k, your energy is minus the dynamical Hamiltonian. And you can define it in this way. And then energy is really what generates dynamics. But at the same time, you have a Hamiltonian that is positive and negative. And what we found, but I'm not showing it here, is that we can then write this energy in the form that we also, very similar to the one we use in classical electrodynamics. Good. So we also need field observables in order to have a complete quantum electrodynamics. These are the electric and magnetic field vectors, the complex one, just for simplicity. And H polarized light is pointing in the y direction. V polarized light is pointing in the z direction. But you can write, so we're interested in the observable for E at position X. And we can put an operator here in front of it. What this operator, we have some flexibility there. What we want is that we have time translation symmetry. So your observable cannot change in time. And it also, when you do a translation, if you put your x-axis, you turn it around, for example, then this should not change. So you have spatial translation symmetry and time symmetry. And then we also want that E squared and B squared, when we integrate over it, gives us the normal energy observable. And this is possible if our R is lambda of X in K space gets this modulus K in there with a square root over it. So this is the, apart from doubling the Hilbert space, this is essentially the standard expression. But then what we realized after a while, what we can do now is, I know what this A is lambda of K is, so I can replace it by its Fourier transform. Then I have an integral over dk and an integral over A is lambdas of X. And then I can do the integration, and then we get an expression for R is lambda of X in X space. And then you get an operator here that is non-local. So what that means is when you have an excitation at X prime, it still generates a field at X some distance away. So, and this is more or less the picture that we have in mind. So we think, as I said before, we think of these blips as people standing in a queue. These can be local and they are bosonic, but they are also having a carry field. So if I have a coherent state of a blip, then that creates a field that is non-zero, not only at the position of the blip, but also is felt over a distance. In this way, the E field, the electric field observables do not commute. They are not bosonic, but the carriers of the light are bosonic. So the trick in order to localize light, what we did is we distinguished the fields from the carriers. So the carriers are bosonic, but the fields that are carrying are not bosonic. So if I have a local blip excitation, I can feel the field everywhere. I can also, as I said before, Maxwell's equations allow us to have localized E fields, but then I need to have blips everywhere, which is also okay. So then I have non-local carriers, but I can get a local field. Initially, we talked about these negative frequency photons as antiphotons, but then we gave up on it because they might be, but this idea of localization should also work for particles that are not photons, but then we wouldn't change the charge, for example, of an electron when we localize it. So we gave up on calling it that. Okay, are there any questions so far, or So shall I continue? Good. Closer to dinner. So I went to a conference recently in Germany, and what they said is, you're essentially doing quantum mechanics with photons. Good, fine. But let's think, do we really do quantum mechanics with photons? So what we have now is we moved the description of single photons, at least, much closer to what we do in quantum mechanics, which we kind of expect because wave-particle duality is one of the big realizations of quantum mechanics. It's a really important observation. So now that we have A is lambda of X operators, I have localized states exactly the same way as I have them in quantum mechanics. And so I can define a state X of a basis state X for a single photon by saying this is A is lambda dagger of X applied to the vacuum state. And these X states are automatically pairwise orthogonal because of the bosonic commutator relations. I can also have momentum states, basis states, by applying the A is lambda tilde of K to the vacuum state. Yeah? And they are also pairwise orthogonal. So yeah, I'm not sure. It didn't say much, but there are quite a few papers where we have more details in there about what we did. And of course, the idea with negative frequency photons, for example, is not new at all. So Dirac was giving a talk about negative frequency particles and photons included in the Royal Exhibition in London or something in the 30s. But he kind of discarded them. But what they did at the time, I read his biography, but I'm not by no means an expert on Dirac. At the time, they used a lot of classical mechanics, and Hamilton mechanics had come along, and that kind of suggested that energies are positive. So that's why he then had Dirac-Z's and filled it up whenever something was negative. There's also Margaret Horton. So when we started publishing papers on negative frequency photons, her papers were already out there and probably helped us a lot to get ours published. Cook, R.J. Cook, he is a name that comes up quite often in quantum optics. Ali Mustafa Sadi, and also John Pendry. They're all using positive and negative frequency photons. Okay, but let's get back to wave-particle duality. Now that we have them, now that we can localize states, we have position and momentum states for photons. And we can now have a wave function of single photons because, yeah, we just superpose, and then you have a wave function psi of x. The only thing you have to take into account is that you can have different directions of propagations present. You can have photons that move apart, or they move, everything of the wave packet moves in the same direction. So you sum over those. And then when you Fourier transform this, you have your psi as lambda. And then you can define position and momentum operators. So we do quantum mechanics with photons. There are more similarities. You have different types of particles in quantum physics, that's fine, yeah. So in case of photons, you have different polarizations. In quantum mechanics, you have particles of different mass. One observation that will be really important in a minute is that photons also have a mass. This is kind of important. People refer to it as the moving mass. Of course, the rest mass of a photon is 0, but you can define a moving mass because your energy is equal to mc squared. Your momentum is h bar modulus k, or h bar k. So the energy is h bar ck. So you can define a mass that's positive so that p equals m times c. Yeah. But of course, photons have no mass, but they have a moving mass, and this will become important in a minute. And in classical mechanics and in standard quantum mechanics, we also have p equals mv. So we have a mass and a velocity and a momentum. But of course, I wouldn't talk about wave-particle duality if it was there. There's also one big difference. When you look more closely at what we are doing, there's one really important difference. In quantum electrodynamics, or photons, they can have a wave packet of any shape. As long as it moves at the speed of light, you're fine. Yeah, it solves Maxwell's equation. So the speed doesn't depend at all on the shape of the wave packet. While when you look at standard quantum mechanics, momentum and velocity are always a kind of the same quantity. They are synonymous. And the mass is fixed is just what connects the two of them. So, which means when you introduce a wave function psi of x of a quantum mechanical particle, you cannot have that particle moving at any speed you want. The the momentum expectation values depend on the shape of the wave packet. So we're still dealing with two different entities, and you're probably guessing what I do next. Yeah, we just said, let's play with the idea, what happens if I do exactly the same what we do with photons with quantum mechanical particles? What do we learn? So, like with photons, let's start in the beginning. Let's ask, okay, I want to describe a quantum mechanical particle in some potential V of x. What is my Hilbert space? And we want to have, like I said before, we want to have consistency with classical mechanics. So in classical mechanics, I need to tell, in order to predict dynamics of any mechanical particle, I need to tell you where the particle is and how fast it's moving. So that means the independent parameters, they have to be independent in my Hilbert space, are x and the velocity. So what I kind of suggest is that our basis states, I forgot the line here, our basis states are states of the form x and v. Of course, that kind of, if you're still awake, that should make you very nervous. But I kind of gave the answer already, what will happen. I can write on this? Just a tiny bit, or better not?
I'm not sure.
Okay. Well, we don't. So, so you will see in a minute that this is actually an assumption that will not get us into trouble. So in order so our thinking here is that if, I'm sure that was mentioned already many times before here, if I have a mechanical system, a simple mechanical system of a particle well defined in position and in having an initial speed, I should be able to describe that with quantum mechanics. But the chances that I can do that are very bad if I don't have that in my Hilbert space. I understand if you all look skeptical right now, but don't worry. It does not. The surprising thing is that this does not get us into trouble. So we are moving closer to boom. So what we will use as basis states for quantum mechanics will be states xv. In order for them to have a meanings, what I need is that if my particle is in x and v, then this has to be orthogonal to a state that is x prime and v prime, unless x and v are both the same. So this gives us this overlap between states, which means we now have a basis states for quantum mechanics. What happens is that the state vector of a single particle now looks a bit more complex because we have more states available. Yeah, we have to now, instead of integrating only from -infinity to infinity, we have to integrate over dx and over dv. Then we have a wave function that doesn't depend only on x, but on x and on v. And then we multiply with xv, yeah? And we call it phase-based quantum mechanics because x and v are our phase-based variables. What we also know from relativity is that we have time and space are some variables that we should treat equally. And by treating x and v equally, we're practically also treating time and position equally. So because if I know how fast something is moving, then I know how much time has passed when it's gone from A to B. Yeah. So now we can construct a position operator. We can design a velocity operator in exactly the same as we always do. The eigenvectors are x and v because they have a defined position and defined velocity, and I put an x in the middle, which is the eigenvalue for. But this is not my momentum operator. My momentum operator, by definition, the momentum is the generator for spatial translations. So my momentum operator is minus IH bar. I integrate over x and v, and I have the derivative d over dx. Yeah. So this is what generates spatial translation. Of course, there's a connection between v and p, as we will see in a minute. But this is my momentum operator, and it's now different from the velocity operator. And we will see in a minute that x and p do not commute, x and v commute, and then we will have a mass operator as well. What I will also need in a minute is another operator, namely the generator, a generator for acceleration, because we will have potentials v of x. So I also need an operator that has a d over dv in there, and we use it in a minute. Yeah. Okay. So important thing is quantum mechanics is not yet lost. Everything is still quantum because we have uncertainty relations. X and v commute because I can choose them completely independently. X and a commute because a acts only on velocity. P and v commute, P and a commute. But x and p do not commute, and v and a also do not commute. Yeah? So, and that means all the Heisenberg's uncertainty relations are still there. Because the reason for why these do not commute is that their basis states are related via a Fourier transform. So that's all fine. So everything stays the same. So then we were thinking of consistency with classical mechanics. So what we want is that the states xv, they should evolve. That took a long discussion, several months, but trust me for a minute. So what we decided to demand is that x and v, these states evolve exactly as in classical mechanics according to Newton's equation. And the advantage of Newton's equation is that in most cases, they're independent of mass. There's no mass in there. So x dot is v, and v dot is given by f of x. If I define f of x as the derivative of the potential divided by 1 over m. So for example, if I have a particle that falls down, and so it's practically, this is the force per mass. That's why this in most cases doesn't depend on the mass. Yeah? So if I'm in free space, for example, then my potential is 0. If I have a particle falling down, then my potential is proportional to the mass. And then this drops out. And if we assume this, and this is what we want, then we can derive a dynamic Hamiltonian that generates exactly this type of dynamics. It looks like we have v times p, and v times p is actually something that comes up in a lot of, or there are a few textbooks where they give the Hamiltonian for the electromagnetic field as c times p. And that always puzzled me. But now we're getting the same. It seems strange, but one of the things we can do is, for example, we can take the observable for the energy, and 1/2 mv squared plus v of x that commutes with this dynamical Hamiltonian. So the classical energy is conserved. And in most cases, it doesn't really matter if you have a conservation law. It doesn't matter in exactly what form you write it. Important is that you look at the Hamiltonian that has the same eigenvectors as, for example, the energy that you want to conserve. Okay. So why it took us so long to work out how to impose consistency between this quantum mechanics and classical mechanics is that there are a lot of problems with Ehrenfest theory. So it actually doesn't really hold. So when we teach quantum mechanics in the second year to our students, we say, oh, everything is nicely consistent because expectation values evolve as in classical physics. I had a look at Ehrenfest's paper, and he put quite a lot of constraints on that. So it says it only works if your particle is quite localized, and for a lot of potentials, it doesn't really work. The other thing is also what why I put this example here is I think we realized that just demanding that expectation values evolve as in classical physics is too simplistic. Imagine you have a quantum mechanical particle that is at this position and at this position, and the red line is your potential. Then if you have some kind of locality, then even if you are a superposition between here and here, there is no force. It will not move. Yeah. So if the initial expectation are that the average, the expectation value for the position is equal to 0, and your initial speed is equal to 0. Yeah. But this situation also occurs if I put the mass in the center here and give it an initial 0 speed. But if I put the particle there, it starts rolling. Yeah. So I think what we don't want expectation values to evolve as in classical physics. That's not consistency with classical physics. And that's also not what we do in electrodynamics. What we want in electrodynamics is that the most classical quantum states, the coherent states, evolve as in classical physics, which is slightly different. Yeah. So what we came up with, and that's why I imposed that condition that I had on the previous slide, we want X and V to evolve as in classical physics, because if I then have a statistical mixture of a particle here and a particle here, actually I have that here. So I have a particle here and a particle here, and I have a statistical mixture of the two, then classically what I would expect is that these stay there. And this one I would expect to roll. So by just saying that I want, if I have a superposition, I want it to evolve as the corresponding statistical mixture, which brings us back to Bohm, but we really realized only that we were doing things similar to Bohm a few weeks ago, not even weeks ago. So I haven't looked much into him yet. So but the classical statistical mixtures, they now evolve as predicted by quantum mechanics by imposing that these X and V evolve with the Hamiltonian that we found. And the reason, of course, is that these states are pairwise orthogonal. So a superposition and a statistical mixture have many similarities. Okay. So, but you probably still feel uncomfortable about X commuting with V and X not commuting with P. So there is something seems broken. And of course, the reason why we get away with this is that if P equals M times V, P does not commute with X, V commutes with X. But if my mass is not commuting with X, then everything is fine. Yeah. So the problem is the mass is no longer just a property of the particle, but that's why I emphasized it so much that photons have a mass. Quantum mechanical particles also need to have a moving mass. Yeah. So we can now introduce a mass operator, which is the moving mass operator. And what we find is that if I say, okay, I have an operator, what do I get when I commute it with my Hamiltonian? And it turns out the only way of the mass being conserved is if a particle moves in free space, if there is no potential. Because then when it moves in free space, then there's nothing that changes the mass. The speed is not moving, kind of everything stays the same. But if as soon as I put it in a potential that depends on x, then we will have some changes to the mass. But that also makes it very easy. How do I get back to standard quantum mechanics? Because the only thing I need to do is, we now need to, in order to get the standard quantum mechanics out, is I just have to impose mass conservation. So I just say, I'm making an approximation. I say my mass is conserved. I replace all the mass operators by an identity. I replace the velocity operator by P over M, because that takes care that when my P changes, that P always equals mv. And then we also want Newton's equation of motion for expectation values, which is why the Hamiltonian changes into something that looks a bit more like 1/2 mv squared plus v of x. So that could mean that the standard quantum mechanics is only an approximation of maybe what we should be doing, but I cannot claim that we can derive quantum mechanics, of course, because it's a very complex theory. But there might be, if we have wave-particle duality, then if we want to have more wave-particle duality, if that's what's happening, then maybe this is an approach. We should allow velocity and momentum not to be synonymous also in quantum mechanics. But it could also be that nature has the idea of mass being conserved and not having a moving mass, and being always the particle always having the rest mass. That would also, then standard quantum mechanics is correct, and the phase-space quantum mechanics would be an approximation. But since the photons have a moving mass, suggests that it's probably worth looking into the possibility that mass is not conserved, but that there should also be a moving mass in standard quantum mechanics. And this is kind of important because when you take the Hamiltonian at standard quantum mechanics and you commute it with the Hamiltonian you get from this phase-space quantum mechanics, they don't commute. Because the commutators of the momentum and the commutator of the velocity operators are behaving very differently. Okay, so we have more wave-particle duality now. So if we take the XV states as basis states in quantum mechanics and in quantum electrodynamics, then now a wave packet of any shape can move at any speed. So I have so many more states available to do quantum physics if I want to, if that's the right approach. So we really expanded the Hilbert space a lot, yeah. The Hamiltonian is also the same, essentially, in quantum electrodynamics and in quantum mechanics, because if I'm in free space, then the dynamical Hamiltonian becomes V times P for mechanical particles. It has positive and negative eigenvalues, because this problem that I was describing, that if something moves to the right, it can also move to the left. So you always have this extra solutions. But all the quantum properties that we've been talking about, interference, all of this is still there because we are having wave functions and so on. So I come to the end now. So what I'm trying to do is, if you take home one message, is that there are different ways of approaching quantization. And it might be worth, if you want to learn more about quantum mechanics, it might be worth to look at quantization in a different way, take a different approach, maybe a more physically motivated one. And that just means quantum, it's still quantum in a sense that I can have superposition states. Yeah, I don't have to have, and if I do, the single particle case is the boring one, but if I bring in identical particles and more than one particles and I have interference, then all the quantum features, entanglement, everything is still there. And if I look at the case without interactions, then I know what the dynamic of the states is. If I have interactions, then thermodynamics can help us in many cases to find out what the interactions look like and so on. And then when I have a system of interacting particles, then I'm far away from any classical physics. Yeah. So we use this physically motivated approach to quantize the electromagnetic field in position space. There are a lot of no-go theorems that tell you you're not allowed to do it. But we broke those rules by allowing for the negative frequency photons. Yeah. So by doubling the Hilbert space, you get around those. And then when we quantize quantum mechanical particles, you find that velocity, mass, and momentum are concepts that need closer looking at. And in general, we suspect that quantum mechanical particles also have a moving mass. And to summarize it with a picture, because it's late. So this is what is our I call it hypothesis because we cannot prove any of this. But what we try to find is a lot of plausibility arguments for why this might be the case. So complexity increases in this direction. And then when you make approximations in phase-space quantum mechanics, you get the standard quantum mechanics back. Standard quantum mechanics is not always consistent with classical mechanics. That's why I made this shorter. Phase-space quantum mechanics is by design consistent with classical mechanics because that's how we construct Hamiltonians. And you have that freedom to design your Hamiltonians in that way. And then we made this box a bit longer because there are systems that we can only describe with quantum mechanics. Yeah. I was aiming for submitting the paper before I come here, but I'm optimistic that it will be still this year. So it's almost complete, but yeah, it always takes a bit longer than you think. But thank you very much.
You get different dynamics. Do you get the same predictions?
So we designed a Hamiltonian in the way that it reproduces the results from classical mechanics. I think the difference is that the mass is not constant. As soon as you have a potential where V depends on X, your mass will not be conserved. So you don't get the same dynamics as in standard quantum mechanics.
I mean probabilistic predictions, like, and remember now I'm from the quantum information foundation.
Yeah.
So it's predictions of the kind, violations of inequalities, those quantum things that we don't get from classical mechanics.
That should all be there.
That should all be there.
Yeah. So for example, the commutators are exactly as in standard quantum mechanics. Yeah. So
Yeah.
for example,
but
if you make entangled states.
Yeah, but X and P. You can do local hidden variables for X and P. So I'm really asking.
Yeah.
Other stuff. Okay.
This I don't know enough about. I think that I might need coffee before I can really think about it.
Thank you. The second question was, can you detect the change in mass?
So this we haven't looked into examples yet. So this is really the first time I talk about this. My suspicion is that quantum mechanics, one of my collaborators is from particle physics, says there are not many particles that are very light. Either they have no mass, like photons, or you have like, you talk about the electrons in an atom. Yeah. But as long as the change of mass comes out as relatively small, it might not be detectable, but we don't know yet. So we're really at the stage where we need to look at examples. Yeah. We have a particle physicist on board, so hopefully he has some ideas. Yeah.
Thank you. Really, really good talk. Again, as I've mentioned, this is something I've been meaning to read for a while. It's been sitting. Oh, the bits on this. Two things I was wondering. First was obviously this has all been done kind of one-dimensionally.
Yeah.
Increasing to 2 dimensions, is it literally just a matter of adding another generacy for sort of forward backwards, or okay, so it's not, because I was worried it might blow up massively if you were to try and do.
Yeah, so we have the students who wrote the first also on the local photons. In his PhD thesis, he has the 3D case.
Ooh, nice.
But there's Huygens principle. So you can introduce blips in 3D. They then travel outwards at the speed of light.
Yep.
But then you have to take care of the Harry-Ball theorem. For anyone who doesn't know what the Harry-Ball problem is. Yeah, imagine a hairy ball, and someone gives you a comb, and your task is to comb the hair along the ball so that it's always orthogonal to the surface. And it's not possible without getting swirls in there. So you get some vortices in there. So, and this is, you have to take that into account in the model. So practically we have 3D blips, and they have a dipole moment. And those dipole moments can be complex. So when an atom emits a photon, that photon that comes out has a dipole moment. So that's actually a property of the light.
Okay.
But then the problem is, when it gets tricky, is when you have many of them, they're all pairwise orthogonal if they are created at the same time. If they are created at different times, we have currently no idea what the interferences looks like. So building out commutator relations for those becomes a lot more tricky.
Okay.
But then maybe for plane waves, you're back to essentially a 1D description.
Yeah.
But it can be done.
Okay.
Yeah.
Good. I mean,
and it's as complex as classical physics, which is
for
not
better or worse.
Yeah.
Yeah. Okay.
But at least not more complicated. If that makes sense.
I mean, second question, you've kind of alluded a little bit to, but also separately, sort of from a use case for this side. Something I remember when I was dealing with a bit more practical optics and things like that is the issues of dispersion, basically, especially when you're trying to deal with wave packets and things in optical circuits and stuff.
Yeah.
Just because mathematically it's incredibly difficult to calculate in quantum optics. So would this be useful as a way to?
Probably yes, because as soon as you localize a wave packet, you have to have positive and negative. I'm not sure. It might be that we really have to look into atom field interactions.
Yeah.
But in principle, you can build in a lot of things into your theory because you're demanding that your expectation values behave in a certain way. Yeah. One of the ideas we had in mind is to look into field quantization in inhomogeneous media, but even in homogeneous, just light traveling into a dielectric, that took us 2 years to write this down. And but Pendry has a nice paper on that. He uses negative frequency photons and there is a community, a nanophotonics community that does a lot of things that people in quantum technology don't seem to be aware of, and they have solved a lot of problems, it seems, already. Yeah.
Thanks for a fascinating talk. Just first of all, how would you implement a measurement of V quantum mechanically different from a measurement of P? So what is the implementation difference?
I don't know. Maybe very similar as in the same problem as in classical physics, I guess. You have a particle here. You know it's here at some time. Maybe you create it here. You need a very precise clock, and then you can look at arrival times. Arrival times would be a measurement of the velocity, not of the momentum.
Okay, but I mean, what you can do when you've got a probabilistic theory generically is that you would have many copies of the system, and in one copy you would wait a time t1 to measure x, and then in another copy you'd wait a time t2 to measure x, and you'd repeat that for an entire ensemble.
You can do that also here.
And then you'd get an expected value of velocity.
Yeah,
right?
But not of momentum.
But
To
okay,
get the momentum, you need a scattering experiment.
but this is what I'm confused by, because at least in classical mechanics, there's a simple MV relationship. So are we? I'm still struggling with that. So what you're basically not just taking m as a constant, and that's the part that I'm having the greatest difficulty with.
So you're kind of velocity and momentum have to be related to each other. And in a good approximation, this classical intuition is probably still right. But when we define momentum, actually, we watched lots of YouTube talks at the time. I don't know where it is. Yeah. The Hamiltonian is the generator for time translation. Momentum is the generator for spatial translation. So it has a d over dx. That means when you have in standard quantum mechanics, when the wave packet has a certain shape, then that fixes the speed. And this doesn't fit with classical mechanics. So if you think of what does it mean to be quantum? Quantum means I can be in different positions at the same time. If mechanics treats x and v on an equal footing, in principle, I should also be able to say how fast are these particles at the different positions moving. And it should not depend on what shape it's like having a car. If you have a Ferrari, you drive this speed. If you have I don't know, something else, a golf like we have, then you drive at a much lower speed, and you can't change it. Everyone can drive at whatever speed they like. Yeah, and if there's a traffic jam, then we all drive at the same speed. So to me, it makes sense that we should have that condition also in. So what we really try to do is to strip all the assumptions that we usually make. Let's make as little as possible, and let's start from what are the basic solutions that we have in classical mechanics that should be distinguishable, and then just build things from there. And then mass is something that changes, which is hard to get used to because that seems to be a property of the particle. But if you say, okay, there are different types of mass, there is a rest mass, and then there is a mass that depends on the speed. I think we haven't looked into applications of this yet, but it feels like a theory that can accommodate relativity in a much more straightforward way in this way.
Yeah, I was just about to ask about that. So in the special relativistic case, does it go over fairly smoothly?
We haven't tried yet.
Okay.
So at the moment, we really design the Hamiltonian in a way by saying, I want Newton's equation of motion, but I can give it other equations of motion, say, what would my Hamiltonian look like? And my Hamiltonian is not really an observable. It's in the first instance, it's the generator for time translation. And that's why it has the role of,
Okay, thank you very much.
If that makes sense. Yeah, but it needs getting used to, and I can't tell whether that's worse or not, but there are lots of indications that seem, sorry.
Thank you very much.